the optimizer team lead at Norvald at MySQL. I have 30 minutes. The topic I'm covering today, I usually spend 3 hours describing, so this will be kind of fast and just scratching the surface, I think, on some things. But I'm going to talk about why we have been building a new optimizer in MySQL. I'm going to talk about what a hypergraph is in a hypergraph optimizer and describe how the optimizer works. And at the end, so that we will sit through the whole thing, I will tell you how to start using it. But first, we're going to do a very quick query processing 101. This is usually a 1.5 hour lecture at the university where I teach as well. But a client sends a query to a server that sends a result back. And the server does a lot of stuff with that query before we can produce the results. We parse the query, produce an abstract syntax tree. We resolve all the table names, column names, we find the views, we expand them into subqueries. And then in the next step, we take those subqueries, we unnest them so that we end up with semi-joins and inner joins for these things. So we end up with hopefully one big query instead of one query with many subqueries. That's because the optimizer itself will only work on one query block at a time, one select at a time. So if a subquery is still left after rewrite, the optimizer will do them independently. So after rewrite, we have something we can call a logical plan, describing what we need to do. The optimizer will figure out how to do that. So this is where we're going to change things with the hypergraph optimizer. So the optimizer decides the join ordering, so table A join with table B or table B join with table A. Are we doing table scan, index lookup, that kind of thing? And are we doing hash join as loop join and all that? So that results in a physical plan saying exactly how to answer that query. From that physical plan, we generate code. We end up with a query program. In MySQL, this query program is not after we have generated our query program, our iterator is MySQL, we execute. This is kind of a textbook way of doing things. In MySQL, we group things together and call them different names. So we say prepare instead of resolve rewrites. We actually call rewriting transformations in MySQL. And code generation is just a very, very thin layer on top of execution. So if you're going to redraw this in the way it works in MySQL 9 today, it looks something like this. We parse, prepare, resolve, transform, and we have two optimizers already in there since 9.0. Actually, in the cloud, it's been there for a bit longer because HeatWave has since at least 8.4 been executing only with the new hypergraph optimizer.
Isn't it in the source code in 8.0?
Sorry?
It's in the source code in 8.0.
Well, it's in development in the 8.0 series and stuff, so it's not complete. But we have two optimizers. The old optimizer is one that is being used for all your queries unless you've done something special. We see that there are two different plan formats there. The old optimizer produces one type of query plan. The hypergraph optimizer produces one type of plan, and we have some transformation steps to convert them so that code generation has one plan format to interpret. This means that the new plan format can express everything that the old plan format can express, but not the other way around. We actually have more options in the new optimizer. So that's a quick overview of where we are in query processing. Let's go to this hypergraph. Or first, the reasons why we create this new optimizer. So this sounds a bit negative. So this is all the things that are wrong with the old optimizer. It is cost-based, but it's not enough. Cost-based enough. It uses heuristics for too many things. It's inefficient in, at least in compared to what we want in selecting join ordering. It doesn't cache cost numbers, so we have to recompute the same cost several times. That's an extra time we can save in the optimization. But also when basically we have to try all valid join orderings for any query to find the best ordering. And that turns out to be an NP hard problem. So at some point you're going to run out of time if you have a big query, and then you have to resolve to go back to heuristics to solve that. And the heuristics of the old optimizer is that you try to build a plan with, as best you can with the tables that can make in that time you have allotted to doing optimization. And then, you say, okay, we're running out of time. Let's just take all the remaining tables, take the smallest one first, then add a join with that one, and join in the second smallest and third smallest, and so on. So it's a very simple heuristic when you run out of time. That's not a good planning yet. Our plans are left heap only, so we can only join in one more table at every step. We can't join table A and B, and then table C and D, and join the join results of those. The old optimizer just can't do that. The plan form doesn't even support expressing that. We don't track interesting orders. This is a huge drawback for us. We actually had to add switches to control that thing, because we can't make a good selection between reading something in sorted order from index or reading something unsorted and explicitly sorting it. Those choices are made, but they're made as like an add-on after doing the join ordering. So it's not a good algorithm for doing that. Hash joins were added late in MySQL, so our choice between nested loop join and hash join is based on, well, first try nested loop join, and in some very safe cases use hash join. So we are underutilizing hash joins, which makes query plans slower in my process. And a real pain point for us was that we have HeatWave, the in-memory distributed column store in the cloud, which is very different from running InnoD on a centralized server on row store. But we weren't able to let HeatWave guide the optimizing and finding a good plan for HeatWave. So that is the problem. We just present HeatWave with a plan that's really made for InnoD with some tweaks. And that's a plan you can execute, but not a good plan for HeatWave. So we need to change that. We have some design goals for the new system that says we want something modern based on current research, on recent research, but not kind of cutting edge experimental stuff. We need something we can rely on, that it's kind of proven. Has to be more cost-based than the old one. We definitely need interesting order tracking. Every optimizer today should have something like that. Good cost-based join algorithm selection. That's also extendable to, let's say, merge join or something in the future. We want bushy plans. Lefty plans are good for a lot of OLTP queries, but as soon as you start with OLAP, bushy plans become a great benefit. And we want the same optimizer for all sort engines. So now we are creating a new optimizer. We want to cover the use cases that we already have. So we have a local row store with InnoD, we have a distributed row store with NDB, and we have a distributed column store with HeatWave. And all those we should actually be able to use the same optimizer for all those. In practice, that turns out to be plugging in different cost models, different cost calculations. So here we are with the Hypergraph optimizer. Let me first show you an overview of the optimizer itself, and then we go into what a Hypergraph is. This is our optimizer. First prepare as before. Then we enter the Hypergraph optimizer, where we construct a hypergraph that we have on the left here. And then we go into a loop where we gradually build a larger and larger query plan to cover the entire query. We do some final touches and then we execute it. I'll get back to this figure. But first, what is a hypergraph? We had to call it something, and one of the kind of distinctive features of this is that we use a hypergraph instead of a normal join graph. So it's a hypergraph optimizer. In this query, we have a left join of T1 with the inner join of T2 and T3. In a traditional join graph, we would say that since we have an on clause between T1a and T2a, there's an edge between table T1 and T2. And there's a join clause between T2 and T3, so we have an edge there as well. But this query can't be executed by joining T1 and T2 first. Because the left join means that we have to kind of include all the rows of T1, and then we don't know what kind of T3 mapping will apply to that join. So we have to do T2 join T3 first. With a hypergraph, which is a generalization where instead of an edge connecting two nodes, we are connecting two sets of nodes. We can say that this join is a join between T1 and the result of T2, T3. So this one has to be done first because this is one side of one hyperedge. So we can actually encode the outer join properties into the graph itself, meaning that whenever we search this graph for the next join to do, we will find this hyperedge and we see that it depends on one side here. So this basically locks in the join ordering of T1 versus this result. So you saw this loop in the hypergraph optimizer. What we do there is that we start with finding all the ways we can access a single table. So let's say we start with T2, we can do table scan, we can do index scan, maybe an index lookup. We do the same thing for another table, let's say T3. We can do table scan on T3, maybe we can do index scan. And then when we have explored all the possibilities for two tables, we can see how we can join them. And then we can propose T2 join T3 with a hash join, T2 join T3 with nested loop join, T3 join T2 with a hash join and nested loop join, and so on. All the possibilities. Once that is explored, we can explore the possibilities for reading T1 with a nested loop, with a table scan or index scan or something. And then we can look at the join itself. So gradually, we are building a larger and larger plan of the query. So if we go back to the optimizer, we try to walk through an optimization. Not a complete one, though. We can start with table A. The red table A up there. We have constructed a hypergraph. Based on join conditions, we have this graph. So table A is our first starting point. We propose a subplan for A. Let's say that is table scan of A. That's always possible. We compute the cost of that. We have a cost model that's storage engine specific or execution system specific. And we compute the cost and we have a list of the best plans we've seen so far. And so far we haven't seen any plans. So table scan of A is the best plan we have for accessing table A. Insert that into that table. We are not done with table A because the next thing we have is an index scan of table A. We have let's say we have an order by clause and we have an index on that column. So we do table scan on that index, compute the cost. As Dimitri showed earlier, that's slightly more expensive than doing table scan. When we get here to update the candidate best plans, we are still accessing table A, but it's more expensive than table scan. But it has an interesting property of providing one of the ordering attributes that we need. So if you have an order by clause on the column that we have an index on, we have an ordering that is interesting to this query. So we will keep that plan as well. Now we have two plans for A, one for unordered, one for ordered access. We go back, and that's all the possibilities for table A. We try table C. We find a table scan, that's always possible, compute the cost, and get back to this evaluation step. We see that this is the only plan we have for table C, so it's obviously the best plan for table C so far. We go back, there's no more options for table C, let's say there's no index. So the next thing we have to do is, can we do something else? We could investigate some other table, but let's say we do the join of table A and C. So we propose doing a hash join between table C and A in that order. We compute the cost. That is the only plan we've seen for that join of table A and C so far. So we insert that into our best plan. It's the best plan we've seen for that particular sub plan. Then we go back and propose more stuff. We can do nested loop join between table C and A. So we compute the cost of that. It turns out to be more expensive than hash join. So we can't insert it into the table because we have a better plan already. So we throw away that nested loop join. We will never think about that nested loop join again, ever. Then we go back and propose the join of C and A, but now in different order. A joined with C with a hash join. Compute the cost. When we evaluate, it seems, okay, this fits the memory as well. So hash join A and A hash join C is the same cost. We already have that in our plan. Okay, throw away this new plan. Never see that again. Then we propose a new subplan. Now it's the nested loop join of A with C, with A as the outer table. Compute the cost of that. And when we evaluate plans, it is more expensive than the hash join we have, but it maintains the ordering of that index scan of table A, since A is the outer table. So now we have a more expensive plan, but it has an interesting property. So we store that as well. And then we continue doing that for every table, every join. And at the end, we have a plan or a set of plans for the entire query, some with orderings, some and one without. And then we make a choice. Do we take the unordered plan and sort it? That has an extra cost. Or do you take something that already produces sorted order? That's what we do in this final step, and then we go and execute. Yeah.
You say that when there is a plan that is not the best one,
Yep.
you forget and never go
Yep.
back. People now can stay force index and stuff like that. Do we still do this, or we just get we don't care?
Yeah. If you use hints, of course, to say that you should do this join order or something, that then we don't really evaluate the cost either. We say, okay, this is what you want. All right. So, if you use hints, of course, you can force it to remember some plan sets that we otherwise wouldn't select. But you came onto a point there that what is better. We have a multi-dimensional cost model. We have 7 dimensions at the moment. It may grow to more. So what I said is the total cost was what I talked about earlier. So the total cost is really what we're trying to reduce here. That's the expectation of execution time. But we also have initialization costs. So if we have on the inner side of a nested loop join, we will read that part many times. And sometimes a plan with a high materialization cost has a really low rescan cost. So materializing a subquery is quite expensive, but rereading that is quite cheap. Maybe we have another plan that really recomputes that thing over and over again that has a lower rescan cost. No, sorry, a higher rescan cost, but a lower initialization cost. So both of them could be relevant to us, depending on how many times we need to reread that subplan. Then we have ordering, at least as we said, this is the interesting order. Everything that you use for order by, group by is interesting. We have some more exotic dimensions as well. Dependency on other tables. So let's say we have a very smart way to read table A, join table B, but it depends on some column that is in table C, so we can't use it unless we have already joined in table C. So parameterized plans that can be used in some special conditions is one option there. Typically, this would be cases for using index lookups in your subplans. Yeah.
Subplan candidates are reused.
Sorry?
Subplan candidates are reused. Like this set of subplans that you already compute are reused for a later match with another plan.
Yeah. So in this plan, we store all the candidates. So yeah. So we have stored this stuff over there, and we can reuse those subplans and when we compute rest. A few more dimensions. We have does our plans produce row IDs that we can use in sorting. So if you sort by row IDs, you can stuff more rows into our sort buffer.
Just one thing to clarify. We are not exhaustively searching all the pairs, right? We are greedily building the plans.
Yeah. But we are kind of exhaustively searching all the joint orderings in the end, if we let this run to finish. But we are guiding it away from plans that are irrelevant. We do evaluate all the joint orderings.
So those will be pruned as we go. Basically.
Yeah, they're pruned out. Yeah. And then we have something for update and delete statements that can be update and delete while we are looking for the rows to update and delete, or do we have to buffer all the changes and apply them afterwards? That's a property that is that affects the runtime quite a bit when it happens. So in this table we have of candidates, we knock things out if they are dominated by another plan. So if there's another plan that is equally good in all dimensions and better in one, then that one knocks out something else. So this will, as I said, run until it ends. It's a bottom-up planner, so we can't really stop. We need to build the entire plan from bottom up. But sometimes that takes too long. So we have a counter for how many times we go around this loop. And if that happens too many times, we resort to heuristics. And not in the way the old optimizer did it. So we don't stop and just add all the missing tables. Instead, we actually abort the entire optimization. We go back and add constraints to our hypergraph. Like I said, one hyper edge kind of locks in one join ordering. But what we can do then is we can look for the most obvious join orderings and lock those in hypergraph. So we find the most obvious choice and we force that join ordering using heuristics. And we do that as few times as possible, but enough so that we are below the limit for how many loops we can do in our optimizer. So then we rerun the optimizer a second time and find the best plan. So once we've done some 100,000 times around here, we found out, okay, this is too bad. We abort, we go back, modify the hypergraph, and rerun this once more. And now the optimizer has used heuristics on the obvious choices and using cost-based decisions on the hard choices. Yeah.
Just a quick question. The statistics and cost models you use, are they completely static during this whole process? Because I guess in theory, they may not, I don't know, I'm just because just to say everything you do is always repeatable with the data.
Within the same query, but like your statistics can be updated between queries.
Yeah,
right?
what I was asking. So,
Yeah.
or is it when you're doing one query that then the values you're looking at are completely stable, so the query will always be, the result will always be the same?
Yeah. Yeah. So this is deterministic, and unless the statistics change, yeah.
Yeah.
Okay, I'm running out of time, so let's do the final slides on how you can start using this. This is what we've been waiting for. As I said, it's in the cloud. It's already there. If you're really using HeatWave, you don't have a choice. You're always using it. We enforced that, and that gave us a tremendous performance boost. If you use InnoDB, you have a choice. If you're running 9.0 or later in the cloud, we have enabled it only in the cloud. We are still working very much on the cost model. The optimizer itself works, it's done, but we are refurbishing our cost model and doing quite a lot of work. Half my team is working on that at the moment. So we do expect quite a number of changes in the cost models, which will affect our plans and stuff. So this is 9 is still in innovation releases, and we are very much innovating in this area. And at some point we'll reach 9.7, where it will be, of course, more stable.
Is the cost model configurable by the user, or is it hard-coded in the code?
At the moment, the cost model is not user configurable. We do expect to add some cost constants that you can tweak as well, but at the moment we don't allow you to tweak them. But there will be new numbers. We don't reuse the old constants that you have for old optimizer. We'll create new entries that we will modify.
I mean, because having that, I mean, even if you expose that, so it's configured, even if, don't touch it because you need to really know what you're doing, it would be nice maybe, because if there are optimizations that you see later, you can then tell people even on an older version, adjust this and maybe.
Yeah. So adjusting these things will, of course, be a good thing to have, although you probably shouldn't touch it.
Yeah.
But we will make sure that, like, we don't want to touch anything for the old optimizer. That is stable. We don't want to disturb it. So all the constants will be new constants in this configuration.
Thank you.
Yeah. Thank you.